This? No?
Now it's too much, yeah.
This?
Yes.
Okay, this one. Can, so should we start? Okay. Yeah, so, well, I originally wanted to do like a talk with slides, but I ended up not doing the slides. But anyway, this is a programming exercise, so maybe to people who like know programming and know logic, everything of this will be just trivial exercise. But I think basically my kind of main connection to the whole thing is that like we use Idris extensively, and we try to like enforce some properties on the code that we write, and this is like well, and Idris itself like gives us tools to to express like category theory and all these more abstract algebraic. So it does it using logic. So basically, this is like a project that that's basically an experiment on encoding some of these logical concepts in Idris. So like having an experience in both and seeing what happens. Yeah. So basically, this produces some actual code you could run. So like this is like writing small interpreters, or you can even call them proto-compilers for a bunch of lambda calculus-based languages, or just variations of lambda calculus. So this is basically what it is about in a nutshell. So I guess what you usually started with is, well, I guess like the whole idea is based on this Curry-Howard isomorphism that basically, like you know lambda calculus, right? Or like who knows like lambda calculus is, or who doesn't know? Okay, so let's say let's say who doesn't know?
How much do you know it?
Like how? Yeah.
Do you know what the word means?
Like how what's the structure? What's
Here to here.
yeah? Okay, so I guess we could start with an untyped lambda calculus then, like real quick. So basically, lambda calculus is like the system that allows you to express like very simple functional programs in it. You could say this, but it's also like this formal system, like formal rewrite system that models computation. So you give it like a term that consists of like several combinators arranged together, let's say, and it computes by simplifying or normalizing that expression until it hits like so-called normal form, or like the place where you simplify it any further. That's basically the answer. So in the simply typed lambda, like untyped, you have like these three components. You have a variable reference, so just like a name of a variable. You have a lambda, which binds a variable in some term, and then you have an application. Not much you can like express on the first glance on this system. So for example, this is like identity. So lambda and you express it just like so. This dollar thing application. So you could say this is so names in here are just some a pair of strings and naturals, but like, we'll probably not use names. So using names is kind of messy. So usually when doing this kind of thing, when encoding this lambda calculi, people usually use at least for like to simplify life for implementers, not the users, maybe the so-called the brain notation. So basically, this means use the variable. So this is the number of like lambda binders you have to skip to get to your variable. So show like on a diagram. Yeah. So basically, like if you have an expression like this, where was it? Oh Jesus, somewhere really far. No? Okay, I can just open it and.
Yeah, view image.
Yeah, so the idea basically is like if instead of having like lambda x, lambda y, lambda z, lambda j, like instead you refer like to the how many lambdas you have to skip over to. Well, we will be using like true programmers like a zero based starting like indexing at zeros. So this would be actually lambda 0, lambda 1, 0. But basically, so this is like if you immediately introduce a binder and immediately refer to it, this is, well, 1 or 0, depending on what you start. So the first lambda.
But
Sorry?
your term has a free variable.
But this basically express only closed ones, I guess.
Only
Well,
closed one.
so this is like basically this how many variables. You can always convert form to another. So the way you can do it is you keep like a dictionary and to the brain. So like if you encounter a variable with some name, then you look it up in some index. So it's like a map of indexes to the how many times, so how many numbers you've already. And in the other cases, you just recurse. And similarly, in the other direction is just looking up in this dictionary, but in the other direction. So, yeah, I mean, basically, then you can encode things like, yeah, this identity term or, let's say, S combinator. So you can also write this so-called Hilbert system, or this is like an thing in proof theory that is equivalent to lambda calculus. But basically, the idea is that this there's this a const function. Like maybe let's look at this one. Yeah, so it has like 2 arguments, and it returns the first argument and ignores the second one. So this is also like a logical const k combinator. Yeah. So and then you can like do things like apply identity or apply like some things to other things. But the problem here is calculus doesn't really have to track what things are applying to other things. So you can like write that don't make sense or like don't terminate. That's also a problem. You can easily write like apply x to x, and that's basically the problem. So in order to kind of fix this thing, you add the system of types, right? So in types, also through the Curry-Howard correspondence, they're like your theorems basically, and the proofs of those theorems, and then the terms of under that type to satisfy the corresponding type. So in simply type lambda calculus, the types you have is, oops. Yeah, basically we'll have like only a single type basically, let's call it A. This is like the base type of everything, or you can have an implication between something to something. So A is a type, and A arrow A is a type, and so on. So you can put those arrows on and on. So this becomes this is the type system basically for simply type lambda calculus. And on the proof theory side, it corresponds basically to logic of propositions, right? So you can either have some fact A or an implication between facts. So yeah, so basically this tells us, or this means that the simply type lambda calculus is basically governed in a type system by this minimal propositional logic. So it's like the Curry-Howard correspondence, like a way to write programs using that logic as a system of rules for your types. So yeah, you can see this here. Basically, now the variable, instead of giving a natural number, you give this indexed proof. And basically, well, first of all, you add like this sequence structure on your terms. So sequence is basically like a relation between a context, so a list of some kind of types of free variables, and the judgment on the type of it. So to construct a variable, you need to know like where is that variable in. So this is exactly the De Bruijn index, just encoded with more structure. So the structure it uses, it's using these linked lists. So linked lists are defined, it's like an address standard database, and they are defined just as inductive structure, right, with two constructors, cons, right? So nil is an empty list, and cons is prepending an element of the list of that. On top of this, you can have a proof, like a constructive proof of that some element is in some specific list. So in address, you write that by adding some, let's say, like replicating the structure of adding some conditional constraints. So like if you have an element A in the list of type A, so how you would write a constructive proof that an element is in that list. So it's either here, then it means that this element X is in ahead of some list. So you enforce that the list in this case would have to be of this form. So it has to be a cons. Or if you have a proof that some X is in list XS, you could say that it also in a list XS but prefixed by another element. So that means when searching for this character, you would throw away the Y and recurse. And so this just indicates the structure of a list. But if you kind of squint on it, this is just a natural number, nat, right? So you could, it's here is 0 and there is just a successor function, right? So this is just basically another way of saying this is a nat, but a nat that is linked to a specific list and a specific that's supposed to be an element of that list. So this is how, so you say like if A is an element of G, which is the context for this term, then this is a term of type GA. Yeah, analogously, so lambda is this constructor for this implication type. So if you have at the top of the context, you have some variable A, and the term produces B, then you can construct, like wrap it a lambda around it and say this is a term which is stripped of this free variable, and the type is the implication or the function. And the application is then the eliminator. So you given a function and an argument for it, you can apply a function to the argument and receive a term of GB, right? So this is basically a simply type lambda calculus. Yeah, you can write functions that forget. So for example, you can just forget all the types and end up basically with the untyped lambda calculus. So this is just removing this element index structure. You can do it very easily by running this thing. So this is just recursing through this here-there proofs and just giving back the zeros and s's. So this effectively just removes all this indexes and just replicates the structure as a natural number, right? So yeah, and similarly, you just forget on lambdas and applications. That's how you like erase all the types. And this no longer allows you to write. So this system is Turing complete anymore. So it doesn't allow you to write like some self-application and basically any non-terminating functions. So all programs with simply type lambda calculus are terminating. And so it's like it's a bit hard to write something meaningful with it. So you can encode numbers in it using this church encoding system, but maybe to make it a bit simpler to look at, you can also encode this so-called PCF thing, which is an extension of lambda calculus with more terms or constructors. So there you have, so this stays the same as in STLC. And then you treat like your base number as a number of unary numbers, and then you kind of like directly in your calculus you have a constructor for zero, successor, and if. So basically this takes 3 arguments. So first the thing you're testing for, if it's 0, then the true branch executes, and if it's false, if it's not 0, then it removes the s from it and feeds it into this term. So it has to have like a free variable of type number. And this has also this fixed point. So now you can again write non-terminating stuff that takes a term with a free variable a and calls the back into this thing.
Is PI the first index in the data type? Is there types of the variables in your context?
Which one?
The very first data, the data term, which is list of types.
Yeah, so this is like a term construct, So like, how would you define a list itself, right? So
I don't mean how you define list, but like this list of types. What does it represent?
this is the context of the term.
Yeah, exactly. So, types
So this is all the types of all the free variables.
yeah, okay.
Yeah. So now, like you can, you can code Idris's natural numbers in this term, or you can also write things like, for example, it's not like very clear here, but you can also write a parser for this, and then you could write like this lambda-like in this lambda-like language. So this is actually subtraction. So this is like yeah. Well, it doesn't have syntax highlighting, but this is basically subtraction in this. So it's a fixed point of PCF, so programmable computer functions. Yeah. Yeah. So this thing. This is, for example, how you would write a subtraction program in this PCF thing. So, like, given a fixed point, like fixes over some variable, and then you have two arguments, x and y, that you're subtracting, like y from x, for example. So, like, if y is 0, then you just return x. Else, you get like y minus 1. So, if y is 0, then otherwise y is of a form s y. So you recurse and remove the inner y. And so then you test if x is 0, then the result is 0. Otherwise, you recurse with x and y, right? So this is how you would subtract, just by pattern matching on the second argument in this case. And this is how you would apply it, for example, to subtract s's. So this is 4 minus 2, basically. So all this thing encodes is, and you have to specify the type because it uses these bidirectional kind of type checking thing. So you can run this. You can compile this into, or you can. I'm not sure if I have it here. Yeah, probably don't. So I mean, this is how you would write the terms. For example, if you have like a term of type plus nats, like a term of implication a to a to a, so it's two natural numbers and adds them. Then how you would apply it? So you would first you apply to the first argument, then you get the function like from a to a. So you apply then the second argument. This is like this currying kind of style. Sorry.
Can you run that down?
Yeah. Yeah. So well, this is all like syntax. So that's what I was going. So this is all basically syntax. How you would like embed this lambda calculus in your or this standard calculus in Idris, but you can also run it, and well, if you go back, for example, to start from this thing is sorry. Basically, you have this recursive function step, which you like run, and it either produces like a result or it's impossible, so you return nothing. So basically, this is a very simple rule. There's only one rule called beta reduction. So it says that if you have a term of a form, wait, sorry, why is my, okay. If you have a term of a form that applies a lambda to some argument, you just replace all instances of that variable inside the body of lambda. So if you apply to the top 0th variable, yeah. I mean, I won't go, why is it, sorry, okay, here we go. Somehow it goes. So you can, this is basically so-called call by step name reduction. So basically, kind of one problem you have in here, this is a bit non-deterministic until you like fix to some reduction strategy. So either you, in case of type lambda calculus, there's a evaluate the argument of a function before feeding it into the function, or you don't. So if you don't, this is like this lazy or call by name evaluation. And if you do, it's these a bit more involved call by value. So call by value usually is like more optimal because it does work like it reduces the argument and then it substitutes already the simplified form of the argument. But on the other hand, it can also basically it can also fail where the call by name would not. And you can, for example, see this. Well, you cannot achieve this really in STLC because STLC never fails; it always finishes. But in PCF, you have this fixed point combinator. And sorry, my laptop is a bit frozen now. For example, you can write a term like this. I thought I wrote it. Oh yeah, BAM. So BAM is basically applies lambda like an identity function, so lambda 0, or just lambda x dot x. So applies an identity. No, sorry, lambda 0 is not. Disregard this. Lambda 0 is a constant function that always returns 0. So it's lambda x dot 0. So it throws away the argument and returns just the number 0. So and there you have a function which is a fixed point over successor itself. So this is well, let's call it mu, like recursion mu x dot sx. So this will like forever keep increasing the number and never terminate, right? So this is doesn't work. So I mean, doesn't terminate. So you can have these small step reductions here. So you have I have this. So basically, it's not important how this goes, but basically, in the call by name thing, like it adds these rules for successor. So if you see a successor, then you add it. If you see if 0, 0, then you just go down the true branch. If you see the successor, then you go down the false branch and the argument, and so on. And if you see a fix, you just go inside fix. Substitute the first argument for the fix again, and run it with let's say BAM, right? So let's say this step. Yeah, so basically in one step, we immediately, in this call by name thing, we immediately get 0, right? Because it didn't try to evaluate the argument, just fed it into this constant function and immediately got 0 out. But instead, if you do this, iter count step iter v, just step v, like it will just hang, right? It will never terminate. Sorry?
I thought you could only write terminating programs at Icarus.
Well, there is this thing in this iter thing. Sorry. So I just I make it kind of believe it is total because just like because if you don't do that, like you have modes of working. Well, yeah, I should probably make a small side excursion into what is this for. But basically, in Idris, since you have you can have arbitrary like code and a type, it's always kind of you want the type to be able to reduce the type and not to wait for it forever or just crash the type checker. So you want the programs you write in Idris by default to be total. So they should always like terminate, and the compiler they should be written in such a form that the compiler can automatically deduce that they terminate. So usually this is achievable by if you pattern match on things, you should if you recurse, you always it's with the argument which is like part of the original pattern. So you just remove some structure and feed it to the recursive function, and that's how a compiler can deduce it's getting smaller and eventually will terminate. So you can override this just by saying like, don't worry, believe me, it's total. So.
So this is actually a built-in inconsistency.
Yeah. Yeah, because yeah, why not? I mean, this means you can like pretend like if you have a problem, you can always like immediately circle down to the functions you lied in. So like if by default everything kind of is supposed to be terminating, you can immediately see okay, must be the critical point.
It's nice to have these things because sometimes you have functions that you know terminate, but
yeah, usually it's used for that.
To prove that they terminate.
Yeah, so usually there's a problem that since this test for termination is essentially just syntactical, like you can write programs which don't immediately, like they manipulate it in a way that well, I can even show you maybe later this code, yeah.
Because of the outing problem, it can't be much better.
Yeah, it cannot be decided automatically, but Idris's type checker could still be better, like there are ways to improve that. Yeah, or you can just this function and just say, believe me, it will terminate, even though you just seen it won't. But now, like, you know why, basically. It's because this only iteration function is that thing that lies to the types checker, and everything else, like, is OK with it. All right, so basically, this is how you would encode this logic in a programming language, like make it into a programming language. Yeah, and this is basically how you run it. So one kind of thing that you can also do, like let me go back to still C. So if you have this small step kind of reduction thing, so yeah, so like maybe to go back a bit though, how is like logic directly? Why is it related to functional programming, and like what's the connection between logic and like this proof theory and functional programming? And yeah, basically the connection is that you use logic for basically the way you could use logic is either you could use it to reason about your code, and that is do, or separation logic. Basically there are like logical tools that are different from the programs that you write. So you write programs in language, I don't know, A, B, C. Let's say you write in C, and then you have like a separate logical tool that's guided by logic that tests like your code outside. Or you could like build the logic into your language with this type checker, and this is basically. And then you also have like two choices, like how to treat computation. So you can say that computation is you treat your programs as these. Terms of this type, so proofs of these theorems. And if you say that I compute by making this proof smaller until they are this normal form, then this is basically functional programming. So this is like called proof normalization as evaluation. But if you decide that instead your computation would be like given a theorem, find a proof for it, this is basically logical programming, or like proof search as a computation. So this is basically how you differentiate from this logical perspective between FP and LP. So is languages like Prolog or SQL, so these things that kind of find a result given some kind of query. So this is so you can apply like this Curry-Howard sort of corresponds to both, but it's just this evaluation mechanism that separates them really at the core. So yeah, and here we kind of reduce these patterns until we arrive at some form. But the problem with this evaluation is it's not what is called tail recursive, right? So in this case, like you step into the argument, or sorry, the function of the application, and then it returns something. Remember, okay, I have to also put back this app thing and pure thing, and then these brackets means that test it's just or nothing, but basically. Yeah, so basically, why is it humming again? Maybe the HDMI thing makes it somehow. Okay. Probably just Idris misbehaving. Yeah, Idris has this problem in tooling that basically there is this IDE process in it that has a small leak in it, and that sometimes you find this soon, sometimes not. But okay, so yeah. This thing is like it's not like tail recursive, and it's not like kind of deterministic. So like you run this thing, and it calls itself, and you don't really know how many steps it did, like until terminating. So usually, like to make it nicer and a bit more predictable, what people do is convert these evaluators to so-called abstract machines. So an abstract machine, well, you could do it in like in two steps. first you say, okay, so in here what happened is basically that like Idris basically has some kind of runtime, or that there's a machine that this evaluates, and that machine has like its own internal stack, right? And when you evaluate it inside the language, like this data gets pushed back, and then that returns, it takes this data of this, construct this thing again. So what you can do is you can internalize the stack and say, okay, I will not use the system stack, but I'll use my own like data structure, like stack-like data structure, and that way like make it tail recursive. So, so the stack is like basically like a list of terms. So this is like a semi-abstract machine, but this is like the first step. So you get this empty stack, or you get a term, and this is, you can also add this indices. So this is like a custom stack that says if you have a term with context G and type A, and you had some G that like ends up at B, but has overall type C, then yeah, you construct like this. You add it and make it like an implication destroyer. So what basically happens here is you remove this recursive step by saying if you have application, like you go down the argument and you put this U thing onto the stack. So in this way, this stack becomes a list of so-called continuations. So it's like the things I have to continue with after like finishing this stuff. And these continuations, they are sort of like counterpart to terms. So this kind of stack thing is like a consumer of functions, basically. That's what it becomes. But yeah, I probably won't talk about that thing. So, but basically, okay, let's focus on this one for that. So this way, yeah, if you see a lambda and you have something on the stack, then you use this substitution functions from before. And yeah, you just have these two rules, otherwise it doesn't reduce. So this is like the first step, but notice we're still using this like external substitution function, which like takes some extra time. So we can trade time for more like space or for my memory, and introduce like a structure to look up these variables in internally. So if we do that, we get like components of our abstract machine, and this is so-called Krivin abstract machine. It's like one of the archetype, probably one of the first like abstract machines defined for lambda calculus. And it's super simple. So basically, stacks. Now you have the three components. You have a term that is you're kind of evaluating. You have an environment, which is like a dictionary of which variables correspond to which terms, and you have the stack, so like continuations, what to do next at each step. So, and you also add like this notion of closure. So closure is like a term and an environment that was like actual when it was created. So like term and its environment. So yeah, an environment is just then a list of these closures, and stack is just a list, again, also a list of disclosures, but yeah, so environment is just for lookup, but stack is just for continuing at every moment. So then you have like to add these two extra rules for variables. So if you're down at the variable that like you're 0, you're at the argument of the argument of the lambda that you're looking at. Then you take like the top thing from the closure. So you take the term as the thing you're now evaluating, and you take this saved environment as the current environment. And otherwise, you just decrease the variable and throw the top thing off the environment. So you like look up into the environment. So this is the Krivin abstract machine. And what you can do, you can extend it again also for PCF. And this is this so-called machine N. Sorry, what?
What is the machine called?
This is basically a Krivin abstract machine, but extended for PCF instead of lambda calculus. And what you do here is a bit more involved, but basically the idea in here is if you have a 0 and like you add extra thing for test for increasing elements and for testing them. So this is the continuation that says like after I'm finished evaluating these subterms, like test them for 0 or not. So yeah, if you have a 0 in a test, you continue with T. If you have a successor and false, you continue with false. Otherwise, you assume that you already did it, and you just set the successor to the stack. And at the end, like when you don't have anything to do except these successors on the stack, you put them onto the final answer. And you can also, so this is called an abstract machine. And you can go even like lower and make it into a virtual machine. And like the main like difference, I think theoretically at least, is that virtual machines instead of, so these terms are still like trees, right? So if you have a, well, you have a variable, it's like the leaf of the tree. If you have a lambda, that's just like a tree with one child, and if you have application, that's like a tree node with 2 children. So ultimately, your lambda terms are binary trees. So you can linearize this into some kind of instruction set. It's not really, I guess, important to show what happens, but basically for each thing you get like a code instruction, and then you link those codes in a sort of a list. Again, it's called a path, or well, I call it path, but people usually call it reflexive transitive closure. So it's basically like a list. Like imagine like these dominoes, and you can add the domino to the list only if like the opposing sides match. So if you have a domino of type I to j, and the remainder of the domino list is jk, then you can stack them and you get a list of ik. So like at every point they have to agree. So yeah, this way you can like say, okay, this instruction basically takes a term of type ga and then makes at the end it will produce like some other combination of type of context and type. But the point is like now this thing is linear, so you can just trivially serialize it. So here's a bunch of stuff that just converts this to some predefined bytecodes. So for example, access lookup in the context is byte 20, lambda is 21, and so on. So now you can compile this. You can make basically a compiler, and the compiler is just like this 6 lines. So it's just the rules for translating this tree into this list. And you can make a virtual machine, and a virtual machine is like exactly that old thing that you had. But instead of terms, it interprets these instructions one by one. So you compile like this thing into a parser and a backend or virtual machine, and you get this. Well, this has like several lambda calculi. Oh, sorry. How do I zoom this in? Maybe I'll use this one. Yeah. So we have run, and we can run. We can compile. So let's try compiling this program that we had. So this is in the PCF language. So subtract like 2 from 4. So you can do run compile test PCF to test bin. Yep. So test bin is there. And now you can run it in this call by name machine, and you can run in the question. But in this case, this terminates. So basically, the strategies can differ on terms that don't terminate, but on terms that terminate, or on total terms like strategies, don't really matter conceptually because they always gave the same answer. But they can have different runtimes. So yeah, that's the perpetual.
Is this with confluence that it only tells you something about terminating terms?
Yeah, pretty much, I think, yeah. No, it's like every execution is the same, so it arrives at the same thing, yeah.
So when you make a mistake and when you enter the very, very slow path, you can recover.
So now you can run this compiled program. Well, yeah, compiled in a sense, just linearized. So like in 42 steps, we've arrived at inc null, so basically 2. So 4 minus 2 is 2. And if we run in call by value, it's slightly longer because just like there's some internal bureaucracy, but it's the same answer, right? So 4 minus 2 is 2.
You're saying like have an empty context? What's the...
Yeah, so basically it says that this is the instruction list that totally is like of type A and empty, it has no variable, it's closed basically, because this one is closed, right? So the type doesn't change. And like if you deconstruct it, also the top instruction also is of the same type. So this is mostly for debugging. So like the thing you're interested in is basically this. Okay, so well, you just output like the print the last. So this is not exactly a compiler. Well, I mean, you could say it's a compiler. yeah, so it's a pair of a compiler and this virtual machine, and this is like the pair of a trivial compiler and a complicated, relatively virtual machine. But usually you want to move things into the other direction. You want like a rather complicated compiler that emits something that is very close to the code of the physical machine. So you have your computer, which has like some code, and you have these virtual machines which simulate other machines. But the closer the target machine is to the actual hardware, of course, the better it will run. Less overhead, at least. So this is basically how you use. This is like the first use, or like the main use of the how type theory or proof theory are kind of married through this logic or this Curry-Howard correspondence to build this term. So one way you could experiment and like use things for findings in proof theory is by changing like this type of this sequent thing. So the thing that types the terms. So one way to do it would be to allow for multiple conclusions, so to say. So if you have a context of 3 variables, and then you have a co-context of continuation. So this basically allows you to type classical logic, and this way you arrive at lambda mu calculus, and that one allows you to basically do things like exceptions. So you could say, using some internal encodings, like throw exception or catch exception at some, so continuation, the number of continuation is basically like the name of an exception. So you throw like into some continuation, and then you can return from that continuation. So you can just have this nonlinear control flow, and or people also call this something like functional go-to statement. But that one is not like basically our today. That's not what I'm going to talk about today. Well, for the remainder of the talk. But you can also switch from this. This is basically corresponds to natural deduction style calculus, but you can also have sequent style calculus. And in that one, basically, kind of the spoiler alert or the TLDR is that sequent calculus is basically how you would write abstract machines. So stacks correspond to coterms in sequent calculus, and terms are just terms in sequent calculus. And this is why basically sequent calculus, well, the idea is that when you write reduction for sequent calculus, it's already tail recursive from the start, because you always have like reduction happen in the top. It's always some term against some coterm, and you immediately know that these two interact in some way or the other. So this is like the second thing. So you could either switch to classical logic, you could switch to sequent calculus representation, but let's probably skip those two. And the other non-standard kind of thing you can do is you can switch to so-called model logic. Okay, so model logic is kind of a thing that's been used relatively a lot for computer science, but it's been pretty much always used. Like when I said that there is this logic about programs, like it was, so you have this FP-LP distinction, and you have like logic not like being embedded into the language. So modal logic is mostly being used in that, like as program logic. So there's, for example, this TLA plus modal checker, which like you write in some modal language a higher level like description of your code, and then it runs like some automatic checks using modal logic on it. But one thing you could do, you could try to directly, if you restrict yourself to this intuitionistic model logic, so usually model logic is classic, so you can, like, as with regular logic, you can restrict to intuitionistic fragments, so no negation, just implication and maybe conjunction, disjunction. So, but yeah, let's just focus on variables and implications. And the third thing you add to the types then is this box modality. So this is basically what model logic adds usually to the logic is this. Well, there are different like flavors of modal logic, but the one that is kind of the default one is so-called the alethic logic or the logic of necessity. So there you have, if you have this, like this minimal modal logic, so you have terms of type, some base type, sorry.
So in the classical setting, you can define the diamond as the not box.
Yes, in classical logic,
Case,
this is not the case.
Maybe you want diamond here as well.
No, actually, usually people do box. So box is like the default one. So basically, usually you have this pair.
I guess you want both.
Yeah, ultimately, yeah, but you have to introduce them separately. Like basically, yeah, the thing is that logic you have these box and diamond. So like the two types. So box is like something is necessarily true, and diamond is something is possibly true. This is the usual interpretation. But if you switch and usually those are like interexpressible. So I think box, some diamond is like not box of not your proposition, and the other way around. So like double negation. But since we don't have negation, those things are kind of independent. So we can just look at the fragment where we only have, for example, box. So usually box, basically the spoiler alert or like the for category theory, it's usually box like behaves like a comonad on your type, and diamond behaves as some kind of monad on your type. That's the usual. So if you use box, that's like a comonad, and you can think of this as you're trying to embed like some kind of sublogic, or like you're trying to embed some things that don't mix. So you kind of split your logic into levels, and you say basically the thing. Well, the only thing we can express in this setting is basically we can say that things under box, if they have free variables, they're also of type box. So like box terms cannot depend on variables from like normal, from intuitionistic context. So this is like the interpretation, like this Curry-Howard interpretation. So it says that there are, yeah, what are the uses? Like even for this kind of thing, you could use this to model meta programming. So that's, I think, one of the first like purely programming kind of use cases for model logic, for this intuitionistic model logic, I think by Frank Fenning. But the idea is there that you treat box as, like if you're writing like a meta-programming system, like you basically have some code that generates some other code. So you use box basically to differentiate the code that you run like at this current stage, and the box code is the code that you produce. And so you don't touch it. You don't want it to depend on any. So once you're done with the current stage of your like meta-programming, you're like, you throw away all the variables. So you don't want any references to them in the box thing. So this is basically like how you model this meta-programming. And but then you can have like two styles of writing the actual terms. So I think the earliest one they invented is called dual context. So there you say. So you add like a second context. So this one is a context that like we had for normal variables, and this is the context for so-called valid variables. So like the ones that are modal. So now basically you always operate on your intuitionistic context, and you add like these two terms, which are basically the introduction and elimination of this box modality. So you can always shut like terms that don't have any. Basically, if you have some assumptions D, you move them, you make them valid, and this kind of works for any context G. And on the other hand, if you had like a boxed term and a term with a free variable in the valid variable, then you can. This is basically like application of things. Sorry, this is not application. This is like wrong word. This is like pattern matching the thing under a box, and use like this unboxed value to immediately compute to plug it into the second term. So you unbox something and try to reuse this thing. And there are different also. There are also kind of settings or like flavors of even this modal logic. So like basically it's what axioms they can express. So one of this ubiquitous aqueous, this is like the simplest modal logic. It's called modal logic K, and like it allows you to express. Well, this is not an axiom anymore, but usually it's called axiom. So a theorem, right? Because we have a theorem of this type, so that boxed. If you have a boxed functions and a boxed argument, you can produce the boxed result, right? So if you have a boxed function from A to B, and so this is basically like a signature of a applicative functor in programming, or yeah, I guess in programming. So you implement this thing by doing two lambdas. So we can actually try to you can try to implement this on the spot. Yeah, I turn my whole what because it's simple to type. So now you have to write a term of this type. So we haven't written anything in there. So now basically you have two arguments. So you introduce this lambda terms. So now what happens is like those two arguments like went into the context, and now we have to construct just something of type box B. And so the only yeah, so we need to destruct like both of those boxes, and then just shed it again on the empty context. So you do this let box. So first we like pattern match on this boxed function. So this is the second because is the variable 0, and this is like variable 1. So this one is here, and this one is there here. So we unbox this one. And now basically we have it in this model context. So now we unbox the second argument. Well, because they got swapped on this kind of context. It's actually the first one here. So let box. So now like both of them are moved into this valid. Sorry. That's wrong. Yeah, so now they are both in this model context, so we can just apply them, and well, yeah, we can apply them and shut the whole thing. So.
What-driven programming?
Yes. Hole-driven development, it's usually called. Well, basically, yeah, you apply like this this thing to this thing, and then you shut it and move it back into. Yeah, it's get moved to the model context. So this is how you implement this axiom K. So there are also like you can add additional axioms. So you can add like you can make it behave like an actual comonad. So you can add axiom 4. So this is like this duplicate, right? So FA is a FFA in a comonad. So like co-multiplication. So you implement it by pattern matching on A and add in shut twice, but in here you have a slightly different rule for shut. So now if you have like model equal context in a model into like equal intuitionistic and model valid context, you can throw away and replace it with any other context. So basically you tweak slightly these production rules, and then you can. This allows you for your logic to be more expressive. So this one allows this axiom 4 or this co-multiplication, and the most expressive one that is like the go-to model logic with this box modality is so-called S4. So it also allows you to do unbox things, so like this extract for a comonad. So yeah, you can write this small step reduction for it, but what's kind of not really yeah. So you also add this construct. You can add the ability to directly reference a modal variable. So now you have like intuitionistic variable, modal variable, and the rest is the same. So, and this allows you basically to write, for example, this axiom T or the eval thing. So this in metaprogramming, this says like take this code that is a meta code and actually run it, evaluate it. So this is how you do it, but now you have a slightly awkward like model variables and this pattern matching kind of style on these modalities. So you can also do what is called Kripke or Fitch style modal calculus, and in there you have like if you do like Kripke style, then basically you say, the usual kind of Kripke semantics for model logic is called the possible worlds. So in intuitionistic context, in intuitionistic setting, you just say world is just a context. So possible worlds is possible context. So how you do, for example, logic K is by saying that your sequence now, they have like your current context and they have a list of like possible contexts. So now for what shut does is like for if you have an empty current context and you have some extra context on this possible context, then you make it the current one. And when you open terms, that means you can skip through several worlds into, well, in a model logic A, that means you just take the current one and you skip over it, and you can use, so you throw away, well, usually you move backwards, so probably easier to say that you throw away your current context and pop it off. The box one, it's the other way around. So basically, this then becomes just manipulating this stack of context. So just saying, I want to, and again, so if you do axiom K, so now like these shut and open things are kind of inverted, right? So in this dual context, you first like open this and then you shut the result.
Possible contexts in a list, and you can operate on it. Then does that restrict the form of your key frame? Like you are just having one list of possible words in front of you.
Yeah.
Usually it's an arbitrary pre-order or that or whatsoever. So maybe you're restricting the form of the words.
Probably, yeah. I'm not really true. I can't say if this.
Also definitely not order.
Well, in here basically they are, and works for this metaprogramming interpretation. So I guess. Yeah, so the interpretation here that this shut and open thing, they correspond like to these quote-unquote metaprogramming operators. So it's basically like saying that I'm going to, which is like quoted, and inside this quoted code you can put these islands of uncoded form that will be, the result of them will be integrated in the stuff that you output. So it's like a macro system, but with types. So this model logic basically types this kind of macro system. Quasi-quoted macro system. And again, so this is, well, in system K, you can only like skip of one world into possible worlds, but if you do S4, that basically means that you can skip an arbitrary like prefix of them. So this is again, I again use this specialized here, there element proof, but this is saying basically that there is some non-empty list of contexts, and it can be prefixed by multiple things, and this just says how many of them. So basically this then says that you can choose which exactly world to open, so you can skip over multiple of them. And so this again allows you to express this axiom T and axiom 4. And yeah, so this is basically how you encode intuitionistic model logic. So you have these two ways, and it's kind of funny because one other thing that you can do, like not really related to model logic, but if you remember, we had these two modes, like strategies of evaluation, right? Like this lazy or like naive lazy call by name evaluation that never evaluated the arguments. And you can have call by value. Well, in practice, there's also this call by need, which is like optimization of call by name. But let's say we have these two, but it's like for our language to be able to kind of decide which parts of the data would be like call by name and which parts will be call by value. So sometimes like you want things to be lazy, sometimes you want them to be eager. So in order to, like in logic, this corresponds to the so-called polarization idea, but it basically says that types can be positive and negative. So so positive ones are, I think, call by value, negative ones are call by name. And you can like switch between them. You can embed them into one another. So the same kind of idea you can apply. I can put the link later into this two encodings of modal logic. So you could say this deconstruction of a box is a kind of a pattern matching. So if you think, like the canonical example for positive and negative data types is pairs, right? So you can, like positive pairs is like a tuple, and that you deconstruct by pattern matching it. So you construct it by giving, so you have a tuple of A and B. Maybe, let me write this. So like a positive tuple is like you construct it by giving A and B, and getting this positive pair of A and B. And you deconstruct it by by saying like match X with A, B in like something that takes A and B and produces some result, right? So it's like pattern matching both members out of it and then immediately doing with them later. But negative style tuple is you see, basically you can, I think you construct it the same way, but the important thing is how you destroy it. So instead of doing this match thing, you have these first and second projections. So like first of AB is A, second of AB is B. So like here you kind of unpack the whole thing and then just and this is kind of the same structure you have with this dual encodings of modal logic. So in dual context one, like you pattern match on this box, and you use it like its contents later. And in the Fitch style or a Kripke style, like you extract, you just project out the first like available world, and here you project out of some number. You choose which one, but still it's like the negative modality. So, and there is like a paper by I don't remember, I can find later, by some people that say you can have like polarized modal logic, and you can have like different styles of this modality elimination, and this way maybe you can get like more expressive metaprogramming language or something like that. So yeah, there are several ideas what also to use this modal logic for. Like one of them is like you could have a type system for a distributed like a program basically. So it would say that box types are the ones that are available on all nodes, and the intuitionistic ones are that available only at current or like node. So you don't want the global variables to depend on local ones, right? So
Maybe you can take the execute factoring name.
yeah, I was actually going.
Modality, and after this kind of firing, you get this kind of value.
Yeah.
I use it in that world.
Yeah, maybe. Like basically, so in general, like modality logic, at least as I understand them, is like something like a way to do some kind of a DSL, to add some kind of notions external to the logic into the logic and try to reason like about those things. So in here as well, it's like just like some kind of syntactic structure, and you choose like when you write the actual virtual machine for it, then you have to choose like which kind of meaning it will have. So either it's like this meta-programming construct, or it's this distributed context, or also like you don't have to restrict to this specific like box and diamond modality. Like for example, another like flavor, I think there's basically 2 or 3 flavors of modal logic most commonly used in computer science, and I think the second one is temporal logic. So basically in there you have like a single modality that means like at the next time tick, or like at the next iteration. And it well, I didn't do that, but maybe I should also, that turns out it's a lambda calculus for this temporal logic. You get like a type system for what's called a reactive programming. So you can like safely express that like at this next step something will happen, and kind of have your program like have a notion of time like internally. Yeah, so, and one other famous modality that exists in like that is known, and I think I've actually historically it was actually invented first, is sorry, where is it? Is linear logic, right? So linear logic is basically a very specific.
S4 was on order.
Yeah, S4 is much older.
Yeah.
Yeah, well, you can basically implement this, at least for intuitionistic, I think, logic. You can implement it like pretty much as S4. But with extra complications on how you deal with context. So basically you have to know how to, in applications, so in eliminators of both the implication and of the bang modality, or well, box called bang modality, like traditionally it's like an exclamation sign. So, well, the meaning of this logic is basically that everything is what's called linear by default, right? So who doesn't know linear logic? I don't know. There are people that don't. But I mean, in this intuitionistic, at least setting, or in programming usually, like this implication means that the variable that you are given, you must use like exactly once, so you cannot like drop it, or you cannot replicate it. And this modality or this bang thing then says like promote or like uplift this linear variable into a intuitionistic variable. So the way you can deal with both is by having these two contexts, so this dual context. And I think historically this dual context interpretation for linear logic was first, and then the model people kind of lifted out. But yeah, so this is exactly like the calculus for the S4 dual context logic. So you have these intuitionistic variables, linear variables. So you can only create. You don't need like an index for a linear variable because you can only create it like at the very bottom. And you also add like these extra complications that when you apply things, you need to, since the context are linear, like you cannot arbitrarily add or remove things from them. You have to like know exactly how to split them into two parts. So that's what happens when you eliminate functions and boxes. You have to know how these things would like split across. But yeah, basically, if you look at the other things, this is exactly like this dual context S4. And yeah, you can write some terms. For example, you can have an identity function, a linear identity function, and you can have a function that has A bang B A, so B can be discarded. So this thing like discards it. Similarly on the other way, so you cannot write these functions because you have no way to like discard to make this context shorter. And yeah, like so basically in model logic, this axiom T is called dereliction, and axiom 4 is called digging. I don't know if this is common terminology, but this is one I found in the paper. You also can copy like intuition banked terms. You can promote banked terms. This is basically like a map. So yeah, this is like this interpretation of like simply typed or model lambda or simply typed linear lambda. But yeah, I'm probably running over time, so I won't bore you much longer. But you can also do like more advanced version of this linear logic by using these graded modalities. So this basically says that this is not like a box is not like a simple single type former. It has like a well, let's say an element of summering or just like a number on it that can many times. So like in this, instead of this bang, which says you can use this 0, 1 or unlimited time, like any amount of time you can have, you can grade it and say like you can use this no more than n times. So the language that does this is called Gryzlou. So yeah, it's open source work by, let me open the paper, Gryzlou project. Yeah, so it's up there on GitHub. So Dominic Orchard, William and Benjamin Lippelt, and Harley Eads III. Wow, okay. So basically, this is this kind of linear lambda calculus, but this is more advanced. So it has all kinds of fancy types, almost as fancy as an Idris. You have like these of dependent types in there, but it also has graded kind of model linear logic. Well, yeah, it's actually more like graded linear logic, but basically there are things that you could do with it, like really interesting things. For example, where is this one? Sorry, this one is. Yeah, for example, basically like a boxed or like unlimited variable A, then you can copy it by basically unboxing it and using it. So if you can use it 0 times, then the only thing you can do is just not use it at all, so drop it. If you can use it exactly 2 times, yeah, then you can copy it again, and you can also like parameterize on it and say things like, sorry, this is just, for example, like this. If you can use a variable a plus 1 times, you can split out like this one usage of a, and the n things will remain. So you can use this to like make this more specific things that you want to express. So one thing, like for example, this linearity could be used for, like potentially, as you know, is this. So you can don't use garbage collector, but instead like you allocate things, you know, in advance how many times, and then you can collect, well, just manually free the memory. So this gives you like more predictable memory usage. There are like lots of usage, of course, you know this better than me, for linear logic, but so this is like a way to write this kind of nicer specifications. So there's also like a lot of work recently to embed things to like integrate model and dependent types. So one of these things is this language. So it's by John Sterling and Daniel Gratzer, I think, and Rob Harbour as well. So in there, you can have, basically it's the same idea. You have the box, and yeah, the box prevents you from depending outside of the box. Dependent types. So, well, in here, like because it's like very limited kind of type system, let me open the other thing. Okay, I don't have it here. So this is like written in OCaml, and yeah, you can have like boxed equality. So x is of type box A, then x. Yeah, so like if x is of type box unlock A, then you have an equality in box unlock A between x and x. Yeah, you can also like say that NAT is, I think it's called a constant. Basically, this means like usually you don't have a function of type A to box A because box is not is a monad, right? So usually you cannot take an arbitrary term and say that it doesn't depend on anything. You cannot box like arbitrary terms. But for some types like NATs, you can do it simply by just recursing down the structure and constructing these boxes. Well, removing and constructing at every recursion step until you end up with one box. Yeah, so this is, well, like this way, there's also like things called the contextual model theory in which like these boxes are also like graded or like a set of variables that are you're only allowed to depend on. So if you have this contextual model theory, it's easier to like model syntax or other like type systems in it. And I think the very latest kind of thing is to have these modalities integrated into homotopy type theory. So in there, I think they use modalities to like say things like this is differentiable, or well, basically there's one even implemented in Agda. It's called Agda flat. So, well, it's like basically it's like a branch of Agda, but it's considered like a dialect of Agda, this Agda flat thing. So it has this, basically it's like this box modality. So you can write in, oh, actually it has been merged into master recently. Okay, so now you have it in proper Agda, probably behind some extension. So yeah, and this allows you to basically have these boxes, but with weird Agda symbols as usual.
But that's not weird.
Well, I mean, not weird for Agda people.
It's not visible.
It's a problem with doing those in Agda. You need to
Oh, it's flat in the sense of
Yeah.
music.
Yeah, it's music flat.
It's really flat.
So,
Yeah.
by the way, how does this relate to the quantitative type theory in Idris? Is that like a graded thing where your grading is only 0, 1, and infinity? Would you say that?
In where? In which one?
So the Idris 2 theory, right?
Yeah.
Quantitative type theory, I think?
Yeah.
So is that like a graded modal type theory
Well,
where your grading is only
not
0, 1, and infinity?
Well, yeah, I think it's sort of graded, but it has like a different meaning. Like the 0 has a special meaning in the sense that this is the thing that you can only use at type level. It's always erased. Yeah, I think it's like an example of a graded one, but in Idris, I think they have like one specific Semmering, like the 0, 1 omega baked in, and then granule it's actually sort of parametric. Well, I think it's like ad hoc. So they have numbers. They also have these privacy level Semmering, which is like basically private and public, or you can have a more complicated like lattice of these access levels. This way you can model this what's called information flow security. So this is basically saying that you cannot like execute this thing with insufficient privileges. Yeah. So I guess this is it.